Okay, hey guys, thanks for having me. So I'm Jiasi, Chen. I'm from UC Riverside. I guess this relates to the discussion that we were just having. I'll be talking about AR and the kinds of work we're doing there and how it can be applied to the Cosmos testbed. I basically have two things I want to talk about. One is more related to some existing work we had, which is going to be more concrete, and I'll tell you about that. And the second thing I was thinking about is a little more open-ended, something I've just recently started thinking about that could be useful in Cosmos. So maybe this is a nice slide to have after that VR discussion, but there are a lot of components in, well, people mix up, first of all, AR and VR a lot, but I think, in my view, they're kind of different. In terms of the components you have in AR and VR are similar, but the emphasis is different. So like Yvonne was saying, the tracking is very important in AR. But here's a rough picture. So maybe you have to track where the user is in the real world. Here we're on campus. You need to detect things that are in space, so you can place a virtual Pikachu on top. You do the placement correctly once you have done the object detection. And then there's the rendering component of rendering the Pikachu to have the right lighting or the right angle to fit in with your real world scene. And then finally you have to do the display in the headset. So yeah, related to VR, VR has all these components as well, but VR probably is a little more heavy on the rendering part, because you have to render the entire scene. But with AR, you just mostly have to render the virtual object that you're placing, like the Pikachu here. So that's my sort of little overview of, I think, the different components of AR. So I think AR is a really good fit for Cosmos, because I know that Cosmos is an outdoor testbed, and I also find it hard to imagine people wearing VR headsets and walking around. But with AR, you think of all the use cases, like Pokemon Go maybe is one example. It's a really good fit, I think, for Cosmos to test these kind of things. So the first thing I'll tell you about is some work we've done on object detection, which is one of the computational bottlenecks that we observe through AR. So when you measure an AR device that is doing all this processing, the object detection is a real problem. It's very slow. So that's one piece of work that we looked at so far. So probably this is I think the next talk is also going to be about this, but it's about edge computing. So how do you use the edge to help with some of those computational bottlenecks in AR? So maybe you guys have probably seen this or understand. I know WinLab also works on similar topics, so maybe there was a similar talk yesterday. But if you want to run some of this computation on the device, it ends up really slow. When we measure things on smartphones, it'll be maybe 600 milliseconds to do this, even with a GPU on the smartphone. So it's really slow. Running the cloud doesn't really work out that well, because you have to send all the data to the cloud for processing and back, and that incurs multiple latency just from the multiple hops. So we don't want to do that. So maybe running on the edge is the right solution. You've probably seen things about mobile edge computing, where you want to run it close to the user so that it has lower latency. So that's basically the piece of work that we did so far. And I will relate this to Cosmos, but first let me get through what we've done so far. So we basically looked at how to run this on the edge compute or not. And so you'd have an input video that would go in. It would get processed on the AR device, and you try to decide where to run this computation, whether to run it on an edge server, whether to run it locally. And then after you've done the processing, say you detected the car, you could put a virtual dinosaur next to it or something. So that was the kind of setup that we had. So you have the device, you have it sometimes connected wirelessly to the edge server, and then the result has to come back to the client to be displayed. So that's the work we did. And we had some kind of computation, decision framework to make all these decisions. Basically, you have a bunch of degrees of freedom that you could use. So whether to offload, the size of or the power of the object detector that you're using. You can also adjust the quality of the video. So whether you encode it at good quality, whether you encode it at low quality, you can change the resolution of the video. All these things can be modified. So you basically have a whole bunch of control knobs here, and you want to do some optimization to figure out what's the right configuration for your device, so that the overall end-to-end latency of the AR app will be low. So you make this optimization, and then you end up with a bunch of metrics. So again, there's some trade-offs between energy, detection accuracy, latency. So you try to figure out how to tune all these knobs so that you get the right kind of performance side, and I guess this is how it relates to Cosmos, is one of the constraints that we use in this optimization formulation are, well, the application requirements, but also like the current network conditions. So, you know, if your network conditions is bad, maybe you want to do all processing locally. If maybe your network conditions is bad, you want to upload the camera frames at a very low resolution or at a low bit rate, because that will save you on time. So we measured all these kinds of frameworks. We measured all these kinds of trade-offs. But what did we do when we evaluated? Well, okay. That was a little example. Okay. So what did we do when we evaluated? We basically had a setup like this, where you had a phone, you had a server, and we just connected over Wi-Fi. And we changed the bandwidth over time with some traces, and we evaluated the performance of the system. So that's like a typical thing that you might do in an evaluation. But what's the kind of typical conference review you have? You get a review that says, your evaluation was only done in a static scenario. What about mobile or dynamic users? That's kind of a typical comment that you can almost say for any paper we review, wireless and mobile. So, and what's our typical author response, which I'm also guilty of, is we do some, you know, toy mobility experiments in the lab where we just walk around a room or a lab space. So what I was thinking is, for Cosmos, is because a key constraint of our optimization problem is the network conditions, how well does that work in an actual urban environment? So if you walk around and you have different kinds of bandwidth and latency and loss rates in an urban environment, is our system able to adapt to that in real time and still provide a good latency? And you might have a question of, okay, why don't we just use existing bandwidth traces? There's a billion of those online. But one thing I'm thinking is that AR users have very different mobility patterns from regular people. So think of like people playing Pokemon Go. They walk around to one place and they stop at the place where they interact with the other users. And then they start walking around to another location, and then they interact with other users. So that'll be a different kind of trace, I'm thinking, than whatever existing ones that are already open source. So that's basically the idea I was thinking in terms of Cosmos for this specific work. And I kind of messed up the order of the slides, but one of the things I've also been playing with, besides just using the regular visual data from the camera, is also using multi-modal data. So you might find, for example, firefighters need thermal cameras to see in the dark and the smoke. So that's beyond regular visible light. So some things we've been playing with recently are, this is an image captured from a Microsoft HoloLens from the infrared camera on the device. And when we pass that through the object detector that I was just showing you, we're able to do some kind of detection. So we want to figure out how to fuse like this piece of information with maybe the regular camera and still provide some good results. So that's a thing we're recently working on. I'm not sure how it fits into Cosmos exactly, but I think it's a fun use case. Okay, so that's like the first piece of work, which is kind of based on existing stuff that we've already published. Something I've been thinking about recently is communication latency for persistent AR, which is the topic of the talk originally. So in that kind of scenario, imagine you have multiple users, and they're looking at some virtual object in the same room on a real table. So maybe on this table, we have placed like a virtual molecule, and I'm wearing my AR headset, and you're also wearing your AR headset. And we'd like to see the same virtual object. So if you want to have that happen, there are multiple pieces of data that need to be communicated between me and you. So when you study like what the AR systems actually do, there are different things that need to be communicated. There's things called anchor maps, point clouds, some interaction data. And when you look at a trace of, this is a bandwidth trace of two users interacting in an AR app. So if you look at what users are actually the devices are actually communicating to each other, you see different kind of traffic patterns. So in this one, you'll see a huge spike when this anchor map is communicated, and you'll see like little blips when, which is when the user is touching the virtual object, and those interactions get communicated to another user. So this information goes over the network, right? So recent problem I've been thinking about is what are the cross-layer interactions between this kind of application layer traffic and like lower layer, like at the MAC layer, like scheduling and so on in wireless. So yeah, that's kind of what I'm thinking about. And I was thinking that Cosmos might be a nice place to try to test out some of the ideas, maybe get some measurements of how these interactions happen and study some problems in this space. So what would I actually need in terms of testbed? Obviously, I haven't thought through fully yet, but the rough setup would be, in both of these examples I was showing you, having like maybe some kind of wireless, some kind of edge compute resources available there in the testbed. We need to have multiple users. I can develop an app, right? Some toy AR app, and have multiple users walking around carrying that app and just hopefully interacting in some reasonable kind of AR-ish way with reasonable mobility patterns. And for the wireless delivery mechanisms, like I don't play directly with like physical layer things, but at least having maybe some kind of, I don't know, LTE simulator or something like that. I guess Wi-Fi is probably easily doable. Maybe different kinds of schedules that are available, or can quickly implement them myself, but just to have a baseline and then play with these apps and see what happens when you interact with the scheduling policies. So that's sort of more where I'm thinking of going. Okay, so that's all I want to say. Yeah, happy to take questions or anything if there are any.